Good morning, everyone. I hope that you had a great weekend and that everybody's doing fine. We're looking today on page 15 of the lesson handout at lesson 30.06, which deals with curved mirrors and the images formed by curved mirrors. This is a lesson that if we were doing it in the classroom, there would be a lot of demonstrations and you'd be able to see a lot of these things firsthand. I'm still going to do my best to intersperse throughout this video a bunch of recorded demonstrations. It's not going to be as good as it would be if you could see this in person, but it will hopefully help you out. To begin with, there are two types of curved mirrors that we're going to be dealing with. So we're not concerned in this course right now with the image that you see of yourself in a bathroom mirror in the morning. That is not a curved mirror. That is what's called a plane mirror, a flat mirror. We're going to be looking at curved mirrors. And there are two types called concave and convex. Okay, we're looking at two mirrors here. The one on the left is a concave mirror. The one on the right is a convex mirror. You can see some images being formed from the convex mirror. What you're looking at is my ceiling. The bright spot of light is a fluorescent light fixture, and the hole in my ceiling is where I'm installing a second fluorescent light fixture. And you can see part of a wall. But you can't see any reflections in the concave mirror on the left. That's simply because of the properties of the mirror. If I put an object on top of the mirror, you can see its reflection there. That's just a little red ball. And just to give you an idea of the shape here, the mirror on the left, the concave mirror, has the reflective side facing the ceiling. And if I let the ball go on one side of the mirror, it will roll back and forth. So it's shaped like a cup. I could pour water in there right now and the water would fill up the mirror. When you look at the convex mirror, if I were to take this ball and put it on top of the convex mirror and give it a little nudge, it will roll off. So the convex mirror has a shape that if I were to pour water over top of it right now, the water would drain off. So hopefully that gives you an idea of what we mean when we say that the mirror is concave or convex. Now, when we are drawing these mirrors, we only typically draw a slice of the mirror. We don't actually draw the whole mirror. So what we're looking at is a side view of just one slice of the mirror. And the mirror on the left is a concave mirror, and a concave mirror has what's called a real focal point, or a real focus. The convex mirror, on the other hand, has what we can call a virtual focal point, or a virtual focus. They both have focal points, but the one on the left is what we call a real one. Now, if you have parallel beams of light that strike this type of mirror, then all of the beams of light will reflect off of the surface of the mirror and they will converge onto a specific point. And it's why I like to call these mirrors converging mirrors. So from now on, concave mirrors can be thought of as converging mirrors. On the other hand, when we take a look at the parallel beams of light coming in from the left on the convex mirror, which is the right-hand side of this frame, all of the parallel beams of light reflect away from each other. They what we call diverge from each other. And if we were to trace back their paths through the mirror, behind the mirror, we would discover that they are all diverging away from a specific point. And that point is the focal point or the focus. So the mirror on the left has a focus where the light reflects to, and that focus is called a real focus or a real focal point. The mirror on the right has a focus that the parallel beams of light reflect away from. And that focus is called a virtual focus or a virtual focal point. And we'll see those words real and virtual again in a minute. All right, there are two types of images that mirrors can produce. They can produce real images and what are called virtual images. Now, before I get to the difference between the two, I need you to understand that both images are things that we see. If you are looking in a mirror at a real image, you will see it. If you are looking at a virtual image, you will see it. I wish they hadn't used the word real here, because to our mind, all images are real. Now, real images are images that can be projected onto a screen, but virtual images cannot. And in order for me to explain to you how we project an image onto a screen and what I mean by that, we're going to take a look at a very, very quick demonstration right now showing a real image. Okay, so this is the setup that we're looking at here, just to show you what a real image actually looks like. I've got 2 meter sticks. The meter stick on the left has a candle mounted on top of it, and the candle is lit. That's what that bright light is. Then in between the 2 meter sticks on the closest end to the camera is a mirror, and you can see some reflection off of the back of the mirror, but that's not the part of the mirror that we're interested in. We're interested in the mirror that's facing the candle flame and also facing the piece of paper that's on top of the other meter stick. So what's happening is the light is moving from the candle towards the mirror, it's hitting the mirror and reflecting off of the mirror, and it's bouncing back to that screen. So I'm going to kill the lights so that we can see what's going on a little more clearly. And even at this setting on my camcorder, you probably can tell that there is some image being projected onto the screen. If I were to zoom in a little bit so we can take a closer look, you can start to make out the fact that it actually looks like a candle. Now, I don't know what the quality of my camcorder recording with this low level of light is going to be, but I'm sitting here in front of this and I can tell that it's not perfectly focused. If I were to move this a little bit closer or further away, I can start to get a clearer image. And my eyes are not that great, but I would say that that's as clear of an image as I can get. And the lesson learned here is you're not just going to get an image wherever you place the screen. There's going to be a relationship between how far away the image is from the mirror and how far away the object is from the mirror. But you can definitely make out that there is an actual image being projected onto the screen, and that's what a real image is. Make a note that the real image is inverted. The candle is pointing upwards and the candle flame in the image is pointing downwards. So in the demonstration that you just watched, we had a little piece of paper that was serving as the screen. If you remove that screen and you put your eyeball at that location, you would see the image of the candle flame. You would see it nice and clear when you looked at the mirror. It would be focused. If we had arranged things so that you were producing a virtual image, and you don't know what that arrangement would involve yet, but if we had a virtual image at that location, and you put your eyeball there, you would see the image when you looked in the mirror. The difference is if you put a piece of paper there instead of your eyeball, nothing would be on the piece of paper. And we'll talk about how virtual images are formed in a minute. Real images are always oriented vertically opposite as the object. Just like in the demonstration, the candle flame was upside down. All real images will be upside down, and we refer to that orientation as inverted. So real images are always inverted, and if you ever see an image that's inverted, it has to be real. Real images are always inverted, and every inverted image is always real. Virtual images are always oriented vertically in the same direction as the object creating the image. So even though we don't really care about plane mirrors today, when you look in a bathroom mirror at your image, you are looking at a virtual image. It is not a real image, which means no matter how hard you try, you could never reflect that image off of the mirror onto a sheet of paper or onto a wall. The word we use to describe that orientation is the image is referred to as erect. So virtual images are always erect, and erect images are always virtual. What that means is the image is oriented one way and the object is oriented the same way. Whereas inverted images, which deal with real images, are upside down. Concave mirrors can produce real images or virtual images. However, convex mirrors only ever produce virtual images. And I want you to use your imagination here. A convex mirror, you know what that looks like by the first demonstration I included here. When you go into a store, you see those security mirrors that they have up in the corners, and they are always convex. And no matter where you are, when you look in that mirror, every image will be oriented the same way as the object producing it, which is why it's very useful for security and safety purposes. Nothing is upside down, so the image is always virtual. You might make a note here, and it might be helpful for later, that those images you see when you look in a convex mirror are always smaller. They always appear very, very, very far away. That's why the mirrors on the side of a vehicle, which are convex, will end up saying objects in the mirror are closer than they appear. They appear very small, so they appear very far away. However, concave mirrors can produce real images or virtual images. And I am going to, after I finish making this video, see if I can figure out a way to film this with my camcorder so that you can see real or virtual images with a concave mirror, but only virtual images with convex. Okay, so what we're looking at is my camcorder on a tripod, and then on some milk crates on either side, I have Yoda on the right and Boxing Nun on the left. So I'm going to be standing on the other side of my yard with a mirror, pointing the mirror at the camcorder, and I'm going to be walking towards the camcorder. And what we want to keep our eyes on is the orientation of the two figures, because we know that if they are oriented upside down or inverted, that means that the image that we're seeing is a real image. But if their orientation is in the same direction, which is called erect, then we know we're looking at a virtual image. All right, I hope that helped you understand the difference between virtual images and real images. Again, one of the points of that demonstration was that the concave mirror can produce real or virtual images, but the convex mirrors only ever produce virtual images. I didn't point it out in my narration in the video, but the virtual images produced by the convex mirror are always small. However, the virtual images produced by the concave mirror are always large. So the magnification for virtual images is quite big if you're dealing with a concave mirror. You can go back and watch that portion again. When I had the concave mirror very, very close to Boxing Nun and Yoda, Boxing Nun and Yoda had images in the mirror that were quite large. So now we're going to move on and look at the equations and the calculations. We start off with this equation which says m equals hi over ho, which is equal to negative di over do. And the first thing I want you to note is that m is the magnification of the image. Magnification refers to is how big the image is compared to the object. So I'm going to write down a total of 4 different magnifications. And I'm not going to write down everything I'm going to say here, but we have 4 magnifications. 2 of them are positive magnifications and 2 of them are negative magnifications. The first thing to note is that since magnification is the height of the image over the height of the object, and height is a vertical measurement, if the magnification is negative, the only explanation is that the object is upside down, because the image would have to be a negative height. So that's one of the things I'm telling you in the course of all this, is that real images, images that are inverted, have a negative height and a negative magnification. However, if I told you that the magnification was positive 2, that's a positive magnification. That would be a virtual image, because positive is indicating that the height is in the same orientation for the image as it is the object. Now, the number itself in the magnification tells you how big or small the object is. A magnification of positive 2 means it is a virtual image that is twice as tall as the object that created it. A magnification of negative 2 means it's a real image which is twice as tall as the object that created it. A magnification of negative 1 over 3 means the image is only 1/3 the height of the object, and the fact that the magnification is negative means it's a real image. I think you get the idea. A magnification of positive 1/3 is a virtual image with a size for the image that's only 1/3 the size of the object. So in these equations, hi is the height of the image, ho is the height of the object, di is the displacement of the image from the mirror. It's a little more complicated than this, but just think of di as how far away from the mirror the image is, and do is how far away from the mirror the object is. I want to point something out to you, that formula that's on this page, m equals hi over ho equals negative di over do, is actually 3 formulas. Its magnification equals hi over ho. Its magnification equals negative di over do, and its hi over ho equals negative di over do. And the last thing I want to say about this equation is when you see that negative di, all that means is negative 1 multiplied by di. Now, the second equation is the focal length equation, and it simply says if you take 1 over the focal length, you have to get the same thing as 1 over the displacement of the object plus 1 over the displacement of the image if you want to get a focused, clear image. Now comes the sneaky part. There's a whole bunch of rules for when things are positive and when things are negative. So here are the rules for the signs. Real images, and by the way, real images are inverted images. These 2 things go together. However, virtual images are always erect images. These 2 things go together. And if you take a look at the heights, the rules for the heights are what I already told you. If you have an image that is erect, that means it's oriented in the same direction as the object, and it has a positive height. But anything that's inverted has a negative height. Now, how is it we remember what the displacements are? I have this basic, simple rule. When you look at, we'll talk about the real images just for a second. When you look at the real images, there is a displacement and there is a height. And when you look at the virtual images, there is a displacement of the image and there is a height. Here's the trick or the rule. For every image, one of those two things is positive and one is negative. So if you can remember that inverted images have a negative, if you can remember that inverted images have a negative height, then that means that they must have a positive displacement. If you can remember that virtual images have a positive height, that means they must have a negative displacement. And then we have rules for the focal lengths. Now, if the mirror is a concave mirror, the focal length is a positive number, but if the focal length is virtual, which it is for a convex mirror, the focal length is negative mathematically. So essentially, real focal lengths are positive and virtual focal lengths are negative. And I want to write that down here. We're talking here for a convex mirror about a virtual focal length, and we're talking about for a concave mirror a real focal length. But don't confuse the focal length with the type of image. A concave mirror has a real focal length, but as we saw in the video I shot in my backyard, a concave mirror can produce real images or virtual images. The focal length of the mirror is a property of the mirror, not a property of the images. So we have to try to keep all of that straight in our head. By the way, what I didn't put in your notes, and I probably should have, is the rules for the properties of the object. And the rule is really, really simple. The height and displacement of the object are always positive. You always have positive properties for the object. So we're going to go through a couple of calculation problems here. The first question says that we have a 3 centimeter tall object. Well, that is a height of an object, that is HO. And we are allowed to use centimeters instead of meters in these equations. It's placed 10 centimeters in front of a concave mirror. Well, that would be the displacement of the object. Focal length of the mirror is 2 centimeters, so F equals 2 centimeters. Now, I'm going to jump ahead to the next question, and then we'll come back to this one in just a second. But one of the things question 2 says is that you have a mirror with a focal length of 4 centimeters. We can write in some other stuff here. The height of the object in question 2 is 2.5 centimeters. The displacement of the object is 9 centimeters, and the focal length is 4 centimeters. And here is the point I want to make. In these mirror questions, you are going to be lied to from time to time. You're told up here that the focal length of the mirror is 4 centimeters. Mirror, which means it has a virtual focal length, so the lie is that you are not told that it is actually negative 4 centimeters. That negative is really important. If you don't use the negative, you will get the wrong answer. And before we do the calculations, which will not take a long time, I want to impress on you this. If you're working on some of these problems and you're getting the wrong answer, even though you think you know what you're doing, it's probably because you missed a negative somewhere. All right, let's take a look at example 1 now and what it is we're asked to find. We're asked to find the characteristics of the image. Well, I guess that would mean we would want to find the height of the image, the displacement of the image, and the magnification of the image. Well, we know F and we know dO. So when we take a look at this equation, we know two of the three variables, so we can solve for dI. Let's take a look at what that's going to look like. It's 1 over F equals 1 over dO plus 1 over dI. So when we put the numbers in, we have 1 over the focal length, which was 2, equals 1 over dO, which is 10, plus 1 over dI. Very important when you solve these to pay careful attention to what I do on my calculator. You never want to rearrange these equations before you calculate. You want to put the numbers in first and do the calculations which lead you to the answer. The correct method in solving this is to start off by taking 1 divided by 2 minus 1 divided by 10. So what I'm doing is I'm subtracting 1/10 from both sides of this equation, and what I get is 0.4. So we get 0.4 equals 1 over dI, which means if you cross multiply, you get 0.4 dI equals 1, or dI equals 1 over 0.4. And you can calculate that on your calculator. You'll get 2.5 centimeters. Now we know what dI is. We can use the formula HI over HO equals negative dI over dO and start putting everything in so that we can find HI. The height of the object was 3 centimeters, so we will have HI over 3 equals negative dI, which is negative 2.5, over dO, which I thought was 10, and it is. And then we can cross multiply to find the height of the image. Now, just before we do that, since dI is positive, that must mean HI is going to be negative. One of them is always positive, one of them is always negative, which means it's going to be a real image. So we're going to take negative 2.5 multiplied by 3 divided by 10. That's going to give us negative 0.75, I believe. But I'm just going to check that. We have 3 multiplied by negative 2.5, then divided by 10. Yep, negative 0.75, and that would be centimeters. So we're almost done. We've got the height of the image, we've got the displacement of the image. The only thing we don't know is the magnification. Magnification can be found using HI over HO, or it can be found using negative dI over dO. I'm not going to do both calculations. You can feel free to do both and see that you get the exact same thing. If I use the heights, the height of the image is negative 0.75 divided by the height of the object, which is 3. By my count, that gives me negative 0.25. And magnification has no units because we took negative 0.75 centimeters divided by 3 centimeters, and the centimeters cancel. So what does this tell us? It tells us that since the magnification is negative 0.75, it's a real image because the magnification is negative, which means it's inverted. And the height of the image is only 25% what the height of the object is. Let's finish this off now with example 2, where we have a 2.5 centimeter tall object placed 9 centimeters away from a mirror with a focal length of 4, but we've already addressed the fact that the focal length is negative 4. So I'm going to set this up for you. I'm not even going to show my work here. You're going to have 1 over F, which is 1 over negative 4, equals 1 over dO, which is 1 over 9, plus 1 over dI. So you're going to have to take 1 divided by negative 4, subtract 1 divided by 9, and then solve for di. Go ahead and do that on your calculator. I'm going to do the same thing on mine. 1 divided by negative 4 minus 1 divided by 9. Don't forget that this is not di, it's the reciprocal of di. So to find di, we have to take 1 divided by the answer, and you get negative 2.77 centimeters. So di is negative 2.77 centimeters. Now we're going to do the same thing that we did last time. We're going to load di into this formula along with HO that we know and DO that we know, so we can find HI. The equation becomes HI over HO. HO was 2.5 centimeters equals negative di. Well, negative di means negative 1 multiplied by di, and di itself was negative. Divided by do, which is 9, so now we're going to cross multiply here. By the way, if you look at what we got for di, we got a negative image displacement, which means the height of the image must be positive, so we'd better get a virtual image. We have to get an object producing an image that is virtual. Cross multiplying here, we're going to take our answer and multiply by negative 1. We're also going to multiply by 2.5 and then divide by 9, which means that we get a height of the image of being 0.77. I'm just going to point something out to you. I always point it out every semester when I teach this, and if you can come up with a logical explanation for why this is the case, I'm really curious to hear it. It turns out that the decimals in DI and the decimals in HI are exactly the same. I put these numbers into Excel, and the decimals go on indefinitely with the same value for both of them. It's just a curiosity. You can take a look at it. The last thing we have to calculate here is the magnification. The magnification can be found by taking HI over HO. That's pretty much what I always do. I don't use the other formula. Not sure why it changed to black there. HI is the 0.77. It's the number on our calculator, divided by HO, which was 2.5. And when we divide those two, we get a magnification of about 0.31, and it's positive. So that tells us that the image is virtual because virtual images have positive magnifications. And it's approximately 30% the size of the object that's producing the image. So I hope you were able to follow those examples. I think this is a very, very difficult lesson for me to teach without us actually playing around with mirrors and light sources and learning from that. I would recommend going to your textbook and looking at some examples there. I hope that lesson went okay. I feel as though I kind of cobbled together as much stuff in the lesson to make it meaningful without making it too confusing. But I guess that remains to be seen. You can give me some feedback next time I talk to you guys. Your homework is on the next page of your lesson handout. Work on number 1, 2, 4, 5, 7, 8, and 9. You can certainly try some of the other problems, but they are challenge problems, and they are really quite challenging. I hope you enjoyed that lesson, and I hope you have a great rest of the day. Don't forget that tomorrow on Tuesday, if you have questions, please show up for the Google Hangout. If you're not the kind of person who feels comfortable being in a Google Hangout, send me an email. But if you need help, please, please reach out to me. I'm more than willing to help you out. So have a great rest of the day, and we'll talk to you guys later.